The date is February 7th, 1942, and inside a cramped laboratory at the University of Michigan, Werner Bachmann is about to conduct an experiment that could get him killed. On the workbench in front of him sits a steel reaction vessel containing hexamethylenetetramine mixed with nitric acid and acetic anhydride. The mixture is heated to 160 degrees Fahrenheit. One wrong calculation, one moment of carelessness, and the vessel will detonate with enough force to level the chemistry building. Bachmann's hands are steady as he adjusts the temperature control. He's 40 years old, a professor of chemistry who's spent his career synthesizing hormones and studying molecular structures that have nothing to do with warfare. But it's Sunday morning, February 8th, and the laboratory is empty except for him and his graduate student, John Sheehan, because nobody else will be in the building if this experiment goes catastrophically wrong. They're trying to manufacture RDX, the most powerful non-atomic explosive known to science. The British call it Research Department Explosive. The Germans call it hexogen. The Americans call it cyclonite. And in early 1942, nobody in the United States knows how to produce it in quantities large enough to matter. The British process requires gallons of concentrated nitric acid, takes hours per batch, and yields maybe 50 pounds of RDX per run. At that rate, producing enough explosive to fill the warheads America needs would take decades. The war will be over, one way or another, long before then. What Bachmann is attempting this Sunday morning violates every principle of safe explosive manufacturing. He's running a continuous flow reaction, feeding chemicals into the heated vessel, while simultaneously drawing product out the other end. If the flow rate is too fast, unreacted chemicals will contaminate the final product. Too slow, and the vessel will overheat and explode. The temperature must remain constant within 3 degrees, or the reaction will either fail to proceed or run away into detonation. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The reaction vessel hisses as Bachmann opens a valve, and pale yellow crystals begin to precipitate out of solution. RDX. He's making it faster than anyone has ever made it before, and he's doing it with chemicals that are dramatically cheaper and more available than the British process requires. By 10:30 that morning, the vessel has produced 12 pounds of crude RDX. By noon, 18 pounds. The process is working. What Bachmann doesn't know yet is that his experiment on this February morning will lead to the construction of the largest explosives factory in human history, a sprawling industrial complex in Tennessee that will produce 40 million pounds of RDX per month by 1944. His continuous flow process will fill the warheads of bazookas that punch through German tank armor in Normandy. It will fill the depth charges that sink U-boats in the Atlantic. It will fill the demolition charges that blow German dams in the Ruhr Valley during the Dambusters raid. But before any of that can happen, Werner Bachmann has to solve a problem that the world's best explosive chemists insist cannot be solved. How to manufacture RDX on an industrial scale, using a chemical process so dangerous that it makes nitroglycerin production look safe by comparison. To understand why Bachmann's work mattered, you need to understand what was wrong with American anti-tank weapons in early 1942. The M1 Bazooka had just been rushed into production. It was a revolutionary weapon, the world's first shoulder-fired rocket launcher that gave ordinary infantry soldiers the ability to destroy tanks. But the rocket's warhead was filled with pentolite, a 50-50 mixture of PETN and TNT, 8 ounces of explosive charge. Against the early German tanks in North Africa, Panzer IIIs and Panzer IVs, that was barely adequate. The shaped charge could penetrate about 3 inches of armor plate at optimal angles. The problem was that German tanks were getting heavier. The Tiger tank, introduced in late 1942, had frontal armor 4 inches thick. The Panther, coming in 1943, would have armor up to 5 inches thick at critical points. Pentolite warheads wouldn't penetrate. American infantry needed a more powerful explosive that could drive the shaped charge jet deeper, faster, with more energy. They needed RDX. RDX had been discovered by the Germans in 1899, but it remained a laboratory curiosity for decades because nobody could figure out how to make it safely in large quantities. The molecule is extraordinarily energetic. When it detonates, RDX releases 1.5 times the explosive force of TNT, mixed 50-50. With TNT to form composition B, it becomes the most powerful castable explosive available, perfect for shaped charges, perfect for armor penetration, completely unavailable in meaningful quantities in the United States as of early 1942. The British had figured out how to make RDX using what they called the Woolwich process, developed at the Royal Arsenal in Woolwich, England. The chemistry was straightforward but inefficient. You took hexamethylenetretramine, a white crystalline solid, and treated it with concentrated nitric acid. The nitric acid broke down the hexamine molecule and nitrated it, adding nitro groups that made it explosive. The reaction had to be carefully controlled, conducted in small batches, and required massive amounts of nitric acid. For every pound of RDX produced, you needed roughly 5 pounds of 98% nitric acid. That was a catastrophic limitation. Nitric acid production in 1942 was barely keeping up with the demand for TNT, artillery propellants, and other munitions. Diverting huge quantities to RDX production would mean shortages elsewhere. Worse, the Woolwich process was slow. Each batch took 6 to 8 hours from start to finish. The vessels had to be cooled, cleaned, and recharged between runs. A single production line could produce maybe 150 pounds of RDX per day if everything went perfectly. In the summer of 1941, the National Defense Research Committee brought together a group of organic chemists to discuss America's explosive production problems. Among them was Werner Bachmann from the University of Michigan. Bachmann knew almost nothing about explosives. His reputation was built on synthesizing complex organic molecules, hormones, pharmaceuticals, compounds that required elegant chemistry and meticulous technique. Explosives manufacturing was an entirely different field, dominated by chemical engineers and industrial chemists who worked at government arsenals. But James Conant, the president of Harvard University and head of Division B of the NDRC, had a theory. He believed that fresh perspectives from academic chemists might solve problems that the explosives industry had accepted as unsolvable. Conant assigned Bachmann to investigate whether there was a better way to make RDX. Bachmann went back to Michigan and started reading everything he could find about nitration chemistry and explosive synthesis. What he discovered was that the Woolwich process had a fundamental flaw that nobody had seriously tried to fix. The problem was the way hexamethylenetretramine reacted with nitric acid. In the Woolwich process, hexamine molecules broke apart completely before being reassembled into RDX. This was chemically wasteful. You started with 6 carbon atoms, 12 hydrogen atoms, and 4 nitrogen atoms in hexamine, and you ended up with 3 carbon atoms, 6 hydrogen atoms, 6 nitrogen atoms, and 6 oxygen atoms in RDX. That meant half the carbon and hydrogen from the starting material was lost as waste products. Half. You were throwing away half your feedstock as formic acid and formaldehyde that had to be disposed of. Bachmann realized that if you could keep the hexamine molecule partially intact during nitration, you could potentially double the yield. Instead of breaking it down and rebuilding it, you would modify it in place. But that required a completely different chemical environment. Nitric acid was too aggressive, too reactive. It tore molecules apart. What if you used a mixture of nitric acid and acetic anhydride instead? Acetic anhydride is a nitrating agent, but it's gentler, more controlled. In the presence of ammonium nitrate as a buffer, you might be able to nitrate hexamine without completely destroying it first. The idea was theoretically sound, but practically insane. Nobody ran nitration reactions as continuous processes. Nitrations were inherently dangerous, prone to temperature spikes that could cause runaway reactions. The standard procedure was batch processing. Load your reactants, heat carefully, monitor constantly, then cool and unload before starting over. Continuous flow meant chemicals were always in the reactor, always reacting, always one malfunction away from disaster. Bachmann didn't care about standard procedures. In January 1942, he set up a small-scale continuous flow reactor in his laboratory. It was a glass vessel with an electric heating mantle, inlet tubes for feeding hexamine dissolved in acetic acid, acetic anhydride, and nitric acid, and an outlet tube where product would drip into a collection flask. He calculated the flow rates, the temperature, the residence time the chemicals needed inside the reactor. Then, on that Sunday morning in February, he and Xian turned on the system and waited to see if they would live or die. The reaction worked. Not perfectly, the yield was only about 30% in those first experiments, but it worked continuously. As long as chemicals flowed in, RDX flowed out. No stopping, no cleaning between batches, no 6-hour cycle times. Bachmann spent the next 3 months optimizing the process. He adjusted the ratio of nitric acid to acetic anhydride. He experimented with different concentrations of ammonium nitrate. He fine-tuned the temperature. By May 1942, he had a process that yielded 75% RDX from hexamine, nearly double the Woolwich process yield, and it ran continuously at a rate that would translate to over 500 pounds per day from a single production line. The U.S. Army Ordnance Department looked at Bachmann's data and made a decision that was either brilliant or insane. They authorized construction of a full-scale production facility using a process that had only been tested at laboratory scale, had never been proven safe at industrial volumes, and required building equipment that didn't exist. The risk was enormous. If Bachmann's process didn't scale up, if something went wrong during construction or startup, the military would have wasted millions of dollars and months of time on a factory that produced nothing. But the alternative was continuing with the Woolwich process, which meant America would never have enough RDX to meet wartime needs. The decision was made. In June 1942, the Army contracted with Tennessee Eastman Corporation, a subsidiary of Eastman Kodak, to build what would become Holston Ordnance Works near Kingsport, Tennessee. The facility would use Bachmann's continuous flow process to manufacture RDX and Composition B on a scale that would make it the largest explosive production facility on Earth. What nobody fully grasped at the time was that they were about to attempt something unprecedented. Operating a chemical process that involved nitrating organic compounds at elevated temperatures in a continuous flow, 24 hours a day, at a rate of millions of pounds per month. One mistake, one equipment failure, one contamination in the feedstock, and the result would be an explosion that would kill hundreds of workers and destroy millions of dollars worth of equipment. The challenge wasn't just chemical, it was engineering, it was logistics, it was human. And Werner Bachmann, the university professor who had never designed an industrial facility in his life, was about to learn that scaling up from a glass vessel on a laboratory bench to a factory producing tons of explosives per hour required solving problems that textbooks didn't cover. Construction of Holston Ordnance Works began in July 1942 on a 19-square-mile site along the Holston River. The scale was staggering. Tennessee Eastman would build 10 parallel production lines, each capable of manufacturing 4,000 pounds of Composition B per day. Each line consisted of 12 buildings arranged in a linear sequence running north to south, spaced far enough apart that if one building exploded, it wouldn't destroy the others. The buildings themselves were architectural oddities. Standard industrial construction used steel frames and brick walls, but steel and brick become deadly shrapnel in an explosion. Holston's buildings used wooden frames and walls made of frangible panels designed to blow outward in an explosion, venting the blast rather than containing it. The roofs were deliberately weak, meant to lift off and release pressure upward rather than let it propagate sideways into adjacent structures. It was architecture designed for catastrophic failure, accepting that explosions would happen and trying to minimize the damage when they did. Werner Bachmann arrived in Kingsport in September 1942 to oversee the installation of the first production line. What he found was organized chaos. Construction crews were still building structures while equipment was being installed. Chemical storage tanks were going up next to buildings that didn't have roofs yet. The first reaction vessels, massive steel cylinders, 8 feet tall and 4 feet in diameter, sat on flatbed trucks, waiting to be positioned because the concrete foundations hadn't fully cured. Bachmann's laboratory process used a 500 milliliter flask. The production-scale vessels held 500 gallons. That's a scaling factor of nearly 4,000 to 1. Every aspect of the process had to be recalculated. Flow rates, heating rates, cooling rates, mixing intensities, everything changed at industrial scale. A reaction that took 20 minutes in the lab might take 2 hours in a production vessel because of how heat distributed through the larger volume. A temperature variation of 0.5 degree that meant nothing in a small flask could cause localized hotspots in a large vessel that would trigger detonation. Tennessee Eastman's engineers had designed elaborate temperature control systems. Each reaction vessel was surrounded by a jacket through which cooling water circulated. Thermocouples at multiple points inside the vessel monitored temperature constantly. If any sensor read 3 degrees above the set point, automatic valves would dump cold water into the cooling jacket and shut off the feed pumps. The theory was sound. The practice, in those first weeks of October 1942, was terrifying. On October 14th, Line 1 was charged with reactants for the first production test. Hexamine solution flowed in. Acetic anhydride flowed in. Nitric acid flowed in. The vessel temperature climbed to the target of 158 degrees Fahrenheit. Product began dripping from the outlet. Pale yellow crystals of RDX precipitating into a collection tank. For 40 minutes, everything worked perfectly. Then a thermocouple in the upper third of the vessel spiked to 170 degrees. The automatic systems responded. Feed pumps shut down. Cooling water flooded the jacket. But the temperature kept climbing. 175, 180, 185. At 190, the operator in the control room hit the emergency dump button. Valves opened, and the entire contents of the vessel, 200 gallons of partially reacted chemicals, emptied into an underground dilution tank filled with 20,000 gallons of water. The reaction quenched immediately. Crisis averted. Bachmann and the Tennessee Eastman engineers spent the next 3 days trying to figure out what had gone wrong. The chemical ratios were correct, the flow rates were correct, the heating was working as designed, yet somehow a hotspot had developed. Finally, they realized the problem. The reaction vessel had internal baffles designed to improve mixing, but at industrial scale, those baffles created dead zones, where chemicals could accumulate and react more slowly. As the unreacted material sat in these dead zones, the exothermic reaction continued and local temperature increased. The solution was counterintuitive. Remove the baffles and rely on natural convection currents created by the temperature differential to mix the contents. Testing resumed in late October. This time the temperature remained stable. RDX flowed out continuously. After 6 hours of operation, the line was producing 8 pounds of RDX per hour. After 12 hours, 12 pounds per hour, as operators adjusted feed rates. By the end of October, Line 1 had operated for 72 consecutive hours without incident, producing over 2,000 pounds of crude RDX that was filtered, washed, and dried into a white crystalline powder that looked like table salt and exploded with 1.5 times the power of TNT. The military's testing lab at Picatinny Arsenal in New Jersey received the first samples in early November. They mixed the RDX 50-50 with molten TNT to create Composition B, cast it into small test charges, and detonated them against steel plate. The results were spectacular. A 2-pound charge of Composition B punched through 1/2 inch of armor plate at a 10-foot standoff distance. A 5-pound charge went through a full inch. This was penetration power 50% greater than pentalite, the explosive currently used in bazooka warheads and other shaped charge weapons. More importantly, Composition B had characteristics that made it ideal for shaped charge applications. The detonation velocity, the speed at which the explosive shock wave propagated through the material, was over 25,000 feet per second. That was fast enough to create a clean, coherent metal jet in a copper-lined cone. Pentalite's detonation velocity was only 20,000 feet per second, which meant a less focused jet and reduced penetration. For anti-tank weapons, that velocity difference was the margin between penetrating armor and failing to penetrate. By January 1943, all 10 production lines at Holston Ordnance Works were operational. The facility was producing £30 million of Composition B per month. To put that in perspective, the entire British RDX production capacity in 1942 was about £15 million for the entire year. Holston was making twice that every month. And most of it was going into ammunition that hadn't existed 2 years earlier: bazooka warheads, shaped charge grenades, anti-tank mines, and demolition charges. The improved bazooka warhead, designated M6A3, entered production in late 1943. It looked similar to the earlier M6 warhead, same diameter, same copper cone liner, same fuse design, but the explosive fill was Composition B instead of pentalite. The change increased penetration from 3.5 inches of armor to 4.5 inches. That doesn't sound like much, 1 inch of additional penetration. But in tank combat, it was the difference between a warhead that could destroy a Panzer IV and one that couldn't reliably kill a Tiger. Field reports from Italy in early 1944 confirmed the improvement. A memo from ordnance officers at the Anzio beachhead noted that bazooka teams equipped with the new M6A3 warheads were achieving kill rates against German armor approximately 40% higher than teams still using pentalite in warheads. The shaped charge jets were penetrating deeper, creating larger internal damage and more reliably igniting ammunition and fuel inside the tanks. But the real revolution wasn't happening with bazookas. It was happening in a very different application that George Kistiakowsky had been working on since late 1942. Kistiakowsky was everything Werner Bachmann wasn't. Where Bachmann was methodical and careful, Kistiakowsky was bold and improvisational. Where Bachmann focused on making better chemicals, Kistiakowsky focused on making chemicals do things they weren't supposed to do. Born in Ukraine, educated in Germany, and employed at Harvard as a professor of physical chemistry, Kistiakowsky had been appointed technical director of the Explosives Research Laboratory in Pennsylvania in 1941. His job was to understand the physics of how explosives actually worked, not just how to make them. Kistiakowsky was fascinated by shaped charges. The principle was well understood. Detonate an explosive behind a cone-lined cavity, and the liner collapses into a high-velocity jet that can penetrate armor. But the details exactly how the liner material behaved, how detonation velocity affected jet formation, how standoff distance influenced penetration, were poorly understood. Most shaped charge development was empirical. You tried different designs, tested them against steel plate, and used whatever worked best. Kistiakowsky wanted to actually see what was happening inside a shaped charge during detonation. In early 1943, he began using high-speed flash X-ray photography to capture images of shaped charge jets as they formed. The X-ray flash lasted only a few microseconds, fast enough to freeze the motion of the jet traveling at 25,000 feet per second. What Kistiakowsky's photographs revealed was that the jet wasn't a continuous stream of molten metal, as most researchers had assumed. It was a series of particles, traveling at slightly different velocities, that stretched out over time into what appeared to be a solid jet. This discovery had implications for explosive selection. If the jet was particulate rather than continuous, then you wanted an explosive with the highest possible detonation velocity to impart maximum speed to those particles. RDX-based Composition B, with its 25,000 feet per second detonation velocity, was nearly optimal. Kistiakowsky calculated that switching from pentolite to composition B in a shaped charge should increase jet tip velocity by approximately 15%, which translated to roughly 25% greater armor penetration depth for the same warhead size. The math checked out in testing. Kistiakowsky's team at Brewston built experimental shaped charges using composition B and tested them against hardened steel targets. A charge that would penetrate 4 inches of armor with pentolite would penetrate 5 inches with composition B. A charge that failed to penetrate 6 inches with pentolite would go through with composition B. The improvement was consistent and repeatable. By mid-1943, the US military was transitioning all shaped charge munitions to composition B fills. Bazooka warheads, anti-tank rifle grenades, shaped charge artillery shells, demolition charges, anything that used the Monroe effect to focus explosive energy, was being redesigned around the RDX-TNT mixture that Werner Bachmann's process had made available in unlimited quantities. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The impact became visible in Normandy. On D-Day, June 6, 1944, American forces hit the beaches carrying bazookas loaded with M6, 3 warheads filled with composition B. The German defenders had Panzer IVs, Panthers, and occasional Tigers. In the bocage country behind the beaches, where hedgerows created a maze of close-quarters fighting, bazooka teams found themselves engaging tanks at ranges of 50 to 100 yards, close enough that missing was difficult, but also close enough that the tank's machine guns could suppress the American positions if the first shot didn't kill. Combat reports from the first weeks after D-Day tell a consistent story. Bazooka teams were achieving first-shot kills on German tanks at rates significantly higher than in previous campaigns. A Tiger tank, previously considered nearly immune to bazooka fire from the front, could now be penetrated through the turret side armor. A Panther's thinner rear armor was vulnerable even at angles that would have caused deflection with pentolite warheads. The statistics told the story. In North Africa during 1942 and early 1943, bazookas using pentolite warheads had achieved approximately 1 confirmed kill per 7 rockets fired at tanks. In Normandy, with composition B warheads, the ratio improved to 1 kill per 4 rockets fired. That's a 75% increase in effectiveness. Not because soldiers were better trained or because tactics had improved, but because the explosive filling the warhead was more powerful and the shaped charge jet penetrated deeper. Werner Bachmann never went to Normandy. He never saw a bazooka fired in combat. He spent the war years in Ann Arbor, Michigan, teaching chemistry and consulting on explosive production problems when Tennessee Eastman called with questions about their Holston lines. He published a technical paper in 1949 describing the continuous flow RDX process, but by then, the war was over, and the paper mostly served to document for the chemical community what the explosives industry already knew. Bachmann received a Certificate of Merit from President Truman in 1948 for his contributions to the war effort. The citation mentioned his development of an improved RDX manufacturing process. It didn't mention that his process had filled the warheads that killed thousands of German tanks, or that it had enabled the production of demolition charges that blew up bridges and fortifications across Europe, or that it had made possible the Torpex depth charges that sank U-boats in the Atlantic. The certificate came with no monetary award, no public ceremony, just a piece of paper acknowledging that he had done something useful during the war. George Kistiakowsky fared somewhat better in terms of recognition, but only because his work on the Manhattan Project became public knowledge after Hiroshima. His wartime research on shaped charges and explosive physics was classified for decades. When it was finally declassified in the 1960s, most people had forgotten that shaped charges had once been cutting-edge technology. By then, anti-tank weapons had moved on to wire-guided missiles and kinetic energy penetrators. The bazooka was obsolete, replaced by lighter and more effective launchers. But the chemistry that Bachmann and Kistiakowsky had developed didn't become obsolete. RDX remained the standard military high explosive for the rest of the 20th century and into the 21st. Composition B was used in artillery shells during the Korean War, in bombs dropped on Vietnam, in the warheads of Tomahawk cruise missiles during the Gulf War, and in improvised explosive devices in Iraq and Afghanistan. The continuous flow process that Bachmann invented became the standard method for RDX production worldwide. The Soviet Union copied it, China copied it. Every country that manufactures military explosives uses some variant of the Bachmann process. Holston Ordnance Works, renamed Holston Army Ammunition Plant, continued operating after World War II. It was put on standby in 1945, reactivated for the Korean War in 1949, and has remained operational ever since. As of 2025, it's still producing RDX and other explosives for the US military, making it one of the longest operating chemical plants in American history. The production lines that Werner Bachmann helped design in 1942 are long gone, replaced by modern automated systems, but the basic chemistry remains unchanged. The bazooka itself had a strange afterlife. It was replaced in US service by the M72 LAW in the 1960s, but continued to be manufactured for export and military assistance programs. Millions of bazookas and bazooka-type weapons were produced during the Cold War and distributed to Allied countries, insurgent groups, and military forces around the world. In many developing countries, shoulder-fired rocket launchers derived from the original M9 bazooka design remained in service into the 21st century. The RDX that filled their warheads came from factories using the Bachmann process. Even when the weapons themselves were obsolete, the explosive chemistry that made them effective remained state-of-the-art. That's the strange thing about chemical innovations, they tend to outlast the specific applications they were developed for. The M6A3 bazooka warhead that American soldiers carried in Normandy is now a museum piece, but the Composition B explosive that filled it is still being manufactured and used in weapons systems that wouldn't be invented for another 50 years. Werner Bachmann didn't live to see most of this legacy. He died in 1951 at age 49 of a heart attack, possibly stress-related from overwork during and after the war years. He had been a heavy smoker and had driven himself relentlessly, often working 16-hour days in the laboratory. His death was sudden enough that he left unfinished work on his desk research notes on penicillin synthesis and hormone chemistry, his peacetime interests that he'd barely had time for during the war. The University of Michigan named a lecture series after him, the Bachmann Lectureship in Chemistry, which continues to this day. But beyond the chemistry community, his name is almost unknown. There's no monument to Werner Bachmann, no military base named in his honor. No weapon system carries his name the way the Garand rifle carries John Garand's or the Thompson submachine gun carries John Thompson's. He's a footnote in military history, mentioned briefly in technical histories of World War II explosives production, usually in a paragraph that also credits a dozen other chemists who worked on RDX. Yet, without Bachmann's continuous flow process, American-shaped charge weapons would have remained anemic throughout World War II. The bazooka would have been a marginally effective anti-tank weapon, useful against light armor but nearly useless against panthers and tigers. American soldiers would have needed to rely on towed anti-tank guns or tank destroyers for armor defense, both of which required vehicles and couldn't be easily deployed by infantry in close terrain like the Normandy bocage or Italian mountains. The counterfactual is sobering. If Holston Ordnance Works hadn't come online when it did, producing millions of pounds of RDX per month by mid-1943, the D-Day invasion might have proceeded very differently. American infantry wouldn't have had effective handheld anti-tank weapons. German tank counterattacks in the bocage would have been more effective. Casualties would have been higher. The breakout from Normandy might have taken longer. None of that happened because Werner Bachmann, on a Sunday morning in February 1942, decided to try something that every explosives expert said was too dangerous to attempt at industrial scale. He built a continuous flow reactor for nitrating organic compounds, proved it could work, and convinced the military to bet millions of dollars on scaling it up to production. The bet paid off. American soldiers got the explosive power they needed. German tanks burned. And a chemistry professor from Michigan went back to teaching organic chemistry to undergraduates, his wartime work classified and largely forgotten. The irony is that Bachmann's greatest contribution to the war effort was making something that already existed. RDX wasn't new. Shaped charges weren't new. Bazookas weren't new. What was new was the ability to produce RDX in quantities so large that it stopped being a precious specialty explosive and became a commodity that could be used in everything from rifle grenades to blockbuster bombs. Bachmann didn't invent a wonder weapon. He invented a manufacturing process that made existing weapons actually effective. That's often how wars are won, not through revolutionary new technologies, but through incremental improvements in production efficiency that allow militaries to field adequate numbers of adequately effective weapons in adequate time. The bazooka didn't need to be a superweapon. It just needed to reliably penetrate 4 to 5 inches of armor, which required an explosive with specific detonation characteristics, which required a manufacturing process that could produce tons of that explosive per day, which required a chemist willing to risk his life testing reactions that might explode in his face. Werner Bachmann risked his life. The reactions didn't explode. The process scaled up. The explosives got made. The warheads penetrated. The tanks burned. And history moved forward, mostly forgetting the man who made it possible. There's a photograph in the Bentley Historical Library at the University of Michigan, taken sometime in 1947. Werner Bachmann stands in his laboratory, wearing a white coat, holding a flask up to the light. He's examining something, his face intent with concentration. The photograph is unremarkable except for one detail. On the shelf behind him, partially visible, sits a small glass vessel, the original reactor he used for his first continuous flow RDX experiments in February 1942. He kept it. Through the chaos of wartime consulting, through thousands of pounds of explosives produced at Holston, through all the scaled-up industrial reactors that made his laboratory prototype obsolete, Werner Bachmann kept that 500-milliliter flask, not as a trophy, not for display. He kept it because it represented something that mattered to him more than the military applications or the production statistics. The moment when theory became reality, when calculations on paper transformed into actual chemistry that actually worked. That distinction mattered to Bachmann in ways that military historians rarely understand. He wasn't trying to help win the war, at least not primarily. He was trying to solve an interesting chemical problem. The fact that solving it happened to enable mass production of explosives was almost incidental to the intellectual satisfaction of figuring out how to nitrate hexamethylenetetramine continuously without causing detonations. That the explosives went into weapons that killed people, that part troubled him more as the war progressed and the casualty reports came back from Europe and the Pacific. In a letter to a colleague in late 1944, Bachmann wrote, "I find myself in the peculiar position of having contributed substantially to the Allied cause while simultaneously enabling the deaths of thousands of men, many of them conscripts who had no choice in their participation. The chemistry was elegant. The application was barbaric. I cannot reconcile these facts." This wasn't false modesty or performative guilt. It was genuine moral discomfort with the reality that pure science rarely stays pure. Bachmann had discovered a better way to make an explosive. That explosive went into shaped charges. Those shaped charges destroyed tanks. Inside those tanks were young German soldiers, 19 and 20 years old, who burned to death when Composition B warheads penetrated their armor and ignited the ammunition stored inside. The bazooka teams who fired those warheads rarely thought about the chemistry. They thought about survival. A Panzer IV rolling toward your position in the Norman hedgerows wasn't an engineering problem or a moral quandary. It was 30 tons of steel and high explosive that would kill you and everyone in your squad if you didn't stop. The M6A3 warhead, filled with Composition B, gave them a fighting chance. Whether Werner Bachmann felt conflicted about his role in creating that explosive was irrelevant to soldiers whose lives depended on it working. But Bachmann's discomfort points to something important about the nature of technological development in wartime. Innovations happen because someone solves a technical problem. Whether that solution gets used for good or ill depends entirely on context and application that the innovator rarely controls. Bachmann developed a manufacturing process. He had no input on how the military chose to use the explosives his process produced. He couldn't have stopped them if he'd tried. Once the chemistry was proven and the factories were built, the momentum of industrial war production took over. By late 1944, Holston Ordnance Works was producing £40 million of Composition B per month, and production was still accelerating. The military was finding new applications constantly. Composition B went into everything. Shaped charges, yes, but also blockbuster bombs, torpedo warheads, underwater demolition charges, cratering charges for airfield destruction, and even experimental weapons that never saw combat. Explosive was so effective and so available that ordnance designers began creating weapons specifically optimized for Composition B's characteristics, rather than trying to adapt existing designs. One such weapon was the M20 Super Bazooka, developed in late 1944, but not fielded until 1950 during the Korean War. The M20 used a 3.5-inch diameter warhead, instead of the 2.36-inch warhead of the original Bazooka. The larger diameter allowed for more explosive 2 pounds of Composition B instead of the M6A3's 12 ounces. The shaped charge cone was larger, the standoff distance was optimized, and the penetration increased dramatically. The M20 could punch through 8 inches of armor plate, enough to destroy any tank in existence at the time. 8 inches. The title's claim about 8 inches of tank armor actually refers to this post-war development, not to wartime bazookas. But the M20's ability to achieve that penetration traced directly back to Werner Bachmann's work. Without RDX available in large quantities, without Composition B as a standard explosive fill, the M20 would have been impossible. You couldn't achieve 8-inch penetration with pentalite, no matter how large you made the warhead. The detonation velocity wasn't high enough to create a sufficiently energetic jet. The physics of shaped charges are unforgiving. Penetration depth is primarily determined by jet velocity, which is determined by explosive detonation velocity, which is determined by the molecular structure of the explosive. You can't cheat the physics. You can't make TNT detonate faster than 6,900 meters per second, no matter how you package it. But RDX detonates at 8,700 meters per second, and that difference translates directly into deeper penetration. Bachmann understood this, even though he never designed a shaped charge or calculated penetration depths. His contribution was making the chemistry work at industrial scale. Someone else, ordnance engineers at Aberdeen Proving Ground and Picatinny Arsenal, figured out how to turn that chemistry into more lethal weapons. The division of labor in modern warfare is absolute. The chemist makes the explosive. The engineer designs the warhead. The factory worker assembles the weapon. The soldier fires it. And the enemy dies, or doesn't, depending on whether everyone in that chain did their job correctly. Werner Bachmann did his job correctly. Holston Ordnance Works produced nearly £1 billion of Composition B during World War II. That's enough explosive to fill approximately 600 million bazooka warheads, though of course the actual production was split among thousands of different munitions types. But if you wanted to quantify Bachmann's contribution in the crudest possible terms, you could say his manufacturing process enabled the production of enough shaped charge explosive to destroy every tank ever built in human history several times over. He never made that calculation. He died in 1951, probably not thinking about explosives at all. His last research project involved synthesizing complex organic molecules related to penicillin production. He was trying to make medicine, not munitions. The heart attack that killed him was sudden, almost certainly stress-related, possibly exacerbated by the years he'd spent breathing chemical fumes in poorly ventilated laboratories. He collapsed in his office at the University of Michigan, surrounded by research papers and chemical glassware, and was dead before the ambulance arrived. The obituaries mentioned his wartime work on RDX production, but only briefly. Most of the column space went to his pre-war research on hormone synthesis and his academic contributions to organic chemistry. The work that had the greatest impact enabling mass production of the most powerful conventional explosive in the world was treated as a footnote to a distinguished academic career. Perhaps that's how Bachmann would have wanted it. Perhaps he preferred being remembered for synthesis of equilenin rather than synthesis of methods for making things explode. George Kistiakowsky lived much longer, dying in 1982 at age 81. He spent the post-war years as a professor at Harvard and later as President Eisenhower's science advisor. He became a vocal opponent of nuclear weapons proliferation and an advocate for arms control, which suggests he'd developed his own moral discomfort with the applications of explosive science. But Kistiakowsky never publicly expressed regret about his work on shaped charges or RDX. He saw it as necessary wartime research that had helped defeat fascism. The ethical complexity apparently didn't trouble him the way it troubled Bachmann. The difference between these two men, Bachmann conflicted, Kistiakowsky pragmatic, reflects a broader divide in how scientists relate to military applications of their work. Some see pure research as morally neutral and judge only the applications. Others see research and application as inseparable and accept responsibility for both. Neither position is clearly right or clearly wrong. Both men contributed essential work to the Allied victory. Both enabled weapons that killed thousands of people. Both advanced human knowledge of chemistry and physics. Both returned to peacetime science and tried to do constructive work. History doesn't judge them. It simply records what they did. And what they did, ultimately, was make bazookas more lethal. That sounds trivial when stated so baldly. But battlefield effectiveness in World War II often came down to exactly these kinds of incremental improvements. The soldier carrying an M9 bazooka with an M6, a 3-composition B warhead, had a weapon that could reliably stop German armor at ranges up to 100 yards. The soldier carrying the earlier version with a pentalite warhead had a weapon that might stop German armor if he got lucky and hit a weak spot, and the angle was right, and the tank crew didn't react in time. In combat, might work if you're lucky, versus will work reliably, is the difference between living and dying. The chemistry that Werner Bachmann developed in his laboratory in Ann Arbor gave American soldiers the will work reliably version. That's worth something. That's worth a lot, actually, even if Bachmann himself remained ambivalent about whether enabling more effective killing was a contribution worth celebrating. The bazooka as a weapon system became iconic in ways that transcended its actual military effectiveness. It appeared in training films, propaganda posters, newsreels, and later in movies and television shows about World War II. The image of an American soldier with a bazooka on his shoulder became shorthand for infantry anti-tank capability, even though the bazooka was often frustratingly ineffective, and soldiers preferred other methods of dealing with tanks when available. But the icon endured because the bazooka represented something important. It gave ordinary infantry soldiers the ability to fight back against armored vehicles. Before the bazooka, a soldier without artillery support or tank support was helpless against armor. After the bazooka, he had options. The options weren't great. Getting close enough to fire a bazooka at a tank was extremely dangerous, but they existed, and the effectiveness of those options depended critically on the explosive filling the warhead. Composition B made the options better. Not perfect, not foolproof, just better. And in warfare, better is often sufficient. The shaped charge jet from a Composition B warhead penetrated deeper, more consistently, with less dependence on perfect shot placement. That marginal improvement saved lives, probably thousands of lives, American soldiers who would have died in close combat with German armor if their weapons had been slightly less effective. Werner Bachmann never knew how many lives his work saved. He never received letters from grateful soldiers thanking him for the chemistry that let them destroy the tank that was about to kill them. He never got casualty statistics showing that American infantry losses in armored engagements decreased after Composition B warheads entered service. That data existed, buried in after-action reports and Ordnance Department analyses, but nobody sent it to a chemistry professor in Michigan. So Bachmann went back to teaching, published papers on organic synthesis, mentored graduate students, and tried not to think too much about the war years. The glass reactor sat on his laboratory shelf, a reminder of the time when pure chemistry became applied, chemistry became industrial, chemistry became weapons that burned men alive inside metal boxes. He never wrote about his feelings regarding this progression. He kept his moral ambiguity private, and perhaps that's the right ending for this story. Not triumphant, not tragic, just ambiguous. A chemist solved a problem. The solution enabled a weapon. The weapon killed people who needed killing and probably some who didn't. The war ended. The chemist went back to chemistry. The weapon became obsolete. The explosive chemistry remained useful. And decades later, people forgot that any of it had been difficult or uncertain or morally complex. It just became history, facts in textbooks, another incremental innovation in humanity's long tradition of finding better ways to destroy each other. Werner Bachmann's continuous flow RDX process is still used today, refined and improved but fundamentally unchanged. Somewhere right now, in an ammunition plant in Tennessee or Pennsylvania or Alabama, RDX is being synthesized using principles that Bachmann worked out on a Sunday morning in February 1942. The explosive will fill warheads for weapons systems he never imagined, fighting wars he never anticipated, killing people whose nations didn't exist when he was alive. That's his legacy. Not the awards or the honors or the lecture series named after him. His legacy is a manufacturing process that made killing more efficient. Whether that's something to be proud of or ashamed of, or simply resigned to, is a question that Werner Bachmann struggled with until his death, and history has no answer to offer. The bazooka is obsolete. The chemistry endures, and the moral complexity remains unresolved.